under a little time crunch here, so I'm going to kind of get right to it. I believe this is page 26. I might have gotten the pages 24 and 26 mixed up. So sine might be 24, cosine might be 26, but either way, get them both in there. Page 26 I'm going to call the sine, and just like we did with the cosine function, we created an XY chart, and we plotted some inputs, and we then plotted some outputs, and we were able to come up with the graph of the cosine function. I'm just going to pick a couple key points here around the unit circle, and remembering that unit circle connects with what we're doing now. We have the big three angle measures in each quadrant, and you should be familiar with those. We're going to start with 0 as an input, and if 0 is the input, we know that sine of 0 is the y-coordinate of that point right there, and the sine of 0 is 0. Remember a couple things we've talked about. The sine gets bigger as you move from 0 radians all the way to pi over 2 radians. And why does it get bigger? Well, because the sine of an angle is the y-coordinate of the point on the unit circle. And so as you move up towards pi over 2, the y-coordinates are getting bigger. And when you get to pi over 2, the y-coordinate is 1. And then notice, as you move from pi over 2 all the way to pi, the y-coordinates are going back down. They're going back down the axis. So when you get to pi, they're back at 0. Okay? And then, as you go from pi radians to 3 pi over 2 radians, so pi radians is here and 3 pi over 2 radians is here, and pi over 2, we just talked about that's up on top. As you move from pi to 3 pi over 2 radians, the y-coordinates are getting lower. And they end up, when you get to 3 pi over 2 radians, the y-coordinates finally get down to -1. And then from 3 pi over 2 to 2 pi, the y-coordinates are going back up from -1 all the way to 0. And so when you get to 2 pi, you get back to 0 again. And that's where we started. Okay, I know we see a 0 here, but we'll look at the graph and I'll explain that. Okay, so let's plot a couple points. We have 0, 0. We have pi over 2, 1. Pi, 0. 3 pi over 2, -1. And then 2 pi and 0. Okay, and so just like this cosine graph, the sine graph is nice and smooth and flowing, and it looks like that. We can plot some points over here as well. I'll let you find those. And we see that the cosine graph looks the same as it did between 0 and pi over 2, or sorry, 0 and 2 pi looks the same as from -2 pi to 0. And so that new term that we've been talking about, the period of the function, we can see that the sine function repeats itself in the same number of radians as the cosine function, so we say the period here is 2 pi, and we'll get down to that in the chart. But there you go, there's the sine function. What you should be noticing is the differences between the sine and the cosine. Where the sine is 0, the cosine is 1, and where the sine is 1, did I point up there? Yeah, when the sine is 0, the cosine is 1, and when the sine is 1, the cosine is 0. Okay? And so we can fill out our chart. The domain of the sine function is the same as the domain of the cosine. It's all real numbers. The range, same range as well. So sine and cosine are very related. From 0 to 2 pi, in fact they are the same graph, just shifted over if you notice that. 0 to 2 pi, we notice that the sine is increasing from 0 to pi over 2. Think about it, the y values are getting bigger from 0 to pi over 2. The y values are also getting bigger from 3 pi over 2 all the way to 2 pi. Don't worry about brackets here, parentheses or brackets are fine. Decreasing, the sine is decreasing only from 0 to 2 pi, it's decreasing from pi over 2 all the way to 3 pi over 2. No horizontal vertical asymptotes, so similar graphs. X-intercepts. So I would challenge you to pause the video right now and see if you can figure out how to acknowledge what the x-intercepts are, or how to write that in the most precise way, concise way. So we start with 0. We could write 0 plus pi k, or we can just write pi k, k is an integer. You want to specify that k is an integer, or just at least understand that k is an integer. K can't just be any real number. So y-intercepts, there's only one, y-intercept of 0. So this should never be more than one y-intercept in a function anyway, so I should probably take that out. Max and min values, the same as the cosine, and the period, again, same as the cosine. Alright, so let's go ahead then and see if we can fit in the tangent into the same video. And the tangent I do know is on page 28. Page 28. And this is the y equals the tangent of x. Okay? And again, x is a real number. We've been finding sine, cosine, tangent of theta. Theta being an angle. Angle in radians is the same as a real number. Okay? So we have the trigonometric function or parent function. Oh man, I've been messing this up. Function family. These should all be different. Switched. Trigonometric should be the function family. The parent function is the y equals tangent x. I guess I did that on the other two as well. So my apologies to you. Alright, well, let's do the same thing we've been doing so you can see the pattern, you can see the reasons why the graph looks the way it does. Okay? Remembering, though, that the tangent of x is equal to the sine of x over the cosine of x. Okay? So if you can remember your unit circle, it really helps you be able to graph these functions. Where the cosine of x is 0, this tangent is going to be undefined. Well, where's the cosine 0? Pi over 2 and 3 pi over 2 is where the cosine is 0. So undefined. Undefined. Okay. Where the sine is 0, that's when the tangent is going to be 0 as well. Well, where is the sine of x equal to 0? The sine of x is equal to 0 at 0 and pi. And so we could there's not a lot here, but where's the tangent equal to 1? Remember, the tangent is a slope. I love that. So Paul Borelli, you get honorable mention here. Tangent is the slope of the line through the origin and the point around the unit circle. Okay, so the slope of the line is 1 through the angle of pi over 4. Okay. The slope is negative 1 through 3 pi over 4. And then we can just stop there for that. So what do we do with this? What do we do when the denominator of a fraction is causing this function to be undefined? Well, what did we do? If you can remember, what did we do when we were graphing rational functions? Well, these provided us with asymptotes. These are vertical asymptotes. Okay, so everywhere the tangent is undefined, we're gonna recognize that to mean that we have a vertical asymptote there. And so we have our vertical asymptotes at pi over 2, 3 pi over 2, negative pi over 2, and so forth. So hopefully put some time and effort into your posters you're making in class, and that you'd be able to see the more of these y values when you plug in more of the x values. And what you should see is a pattern in which goes through the origin, because the tangent of 0 is 0, and then as x gets closer to pi over 2, that ratio of sine to cosine gets bigger and bigger. So you get a bigger and bigger number. In fact, there's no limit to how high that can get. And then it comes down here like that. So that's one, actually that's one period of the sine function. So the tangent function, the tangent function repeats itself every how many radians? I'm not going to give that to you. I want you to think about that. So it looks the same every single time. Notice that you know where the tangent is equal to 0. The tangent is equal to 0 where the sine is equal to 0. So that's really, really important, because the students that mess this up are the ones that think that the cotangent and the tangent have the same x-intercepts. And that's a big mistake. Okay, so we'll get into that in class. But every single one of these points, let's see if I can do this. please listen carefully here. So this is where the sine of x is equal to 0. Right there, there, and there. And where the numerator of the tangent, so this tangent is sine over cosine, when the numerator is 0, the tangent is 0. So the cotangent being cosine over sine would mean that the cotangent doesn't have the same x-intercepts as the tangent does. So keep that in mind. Nor does the cotangent have the same vertical asymptotes as the tangent function. So I want to stress that because those are the mistakes I see made all the time. And we'll talk about cotangent and the other reciprocal functions in class. But for right now, if I can get you to be able to graph sine, cosine, tangent, I'd be a happy guy and you would be right where you need to be. So let's go ahead and look at the domain. The domain is all real numbers x such that x does not equal, see if you can figure out how to write this. Maybe pause the video. Does not equal k times pi, k and integer. So I left the word is out on that one. The range is all real numbers. Increasing. So increasing over one period, we're going to go from negative pi over 2 to pi over 2, and it's increasing over the entire part of that domain. So from negative pi over 2 to pi over 2, the tangent function is increasing. By the way, the tangent function is never decreasing. Horizontal asymptotes we have none, but we finally get some vertical asymptotes for one of these, and these would be, see if you can pause the video now and figure out what I'm going to write. Vertical asymptote would be pi over 2 plus pi k, or k pi, it doesn't matter. K and integer. What do you think through that? X-intercepts, again, pause the video, would be pi k, k and integer. I wouldn't be too upset if you left off k and integer as long as you wrote it once. Y-intercept is 0, maximum value none. You know, if you have a range of all real numbers, there's no way you can have a max or a min value. Okay, periodicity. So the tangent repeats itself every pi radians. I will see you in class. Have a great day.